Large language models can pass the uniform bar exam and generate highly complex code, leading many to assume they possess actual reasoning capabilities. Yet these same models routinely fail to execute basic logical deductions. When Google first demonstrated its BARD model, the system confidently asserted that the James Webb Space Telescope took the very first pictures of exoplanets. It was a complete factual fabrication, an error that temporarily erased $100 billion from Google's market value. Even when equipped with external retrieval systems, models display severe context blindness. An AI recently claimed Barack Obama was the first Muslim president of the United States, simply because it ingested the rhetorical title of an academic book without understanding its premise. Linguists and computer scientists classify this behavior under a formal academic term, the stochastic parrot. The term was coined in a foundational 2021 paper co-authored by researchers including Timnit Gebru, who argued that these models successfully mimic human text while completely lacking comprehension of the underlying concepts. Mathematically, a language model is an engine designed for next token prediction. It stitches together linguistic forms based on the probability weights of how words combine in its training data, operating entirely without a persistent internal model of the real world. Because they lack epistemic grounding, language models do not compute truth. They calculate the likelihood of a sequence, making them mathematically bound to generate plausible but fictitious statements. When an LLM fails a logic task, the software industry's default workaround is to prompt the model to review its own output, or ask it to think step by step. A joint research effort from DeepMind and the University of Illinois investigated whether this intrinsic self-correction actually works. The researchers found that relying solely on the model's inherent capabilities to correct reasoning errors is ineffective. Without external factual feedback, models cannot reliably evaluate the correctness of their own responses. This diagram illustrates the failure. With no independent mechanism to verify facts, self-correction forces a new probabilistic guess using its own flawed context. Instead of fixing the error, trying again actively degrades the final answer. Truthful logic cannot be extracted from a system that only knows probability. It must be injected from the outside. A persistent engineering misconception in AI development is the belief that fine-tuning a model will eliminate its hallucinations. Fine-tuning specifically adjusts the internal weights of the neural network. It trains the model to adopt a specific domain vocabulary, match a certain tone, or format outputs in a desired structure. This split screen illustrates the architectural difference. Grounding, through retrieval-augmented generation, connects the model to external data during a query, injecting verifiable facts. Internal adjustments on the left rely on a static training snapshot that goes stale. Grounding bypasses this by querying live databases for current information. Fine-tuning dictates the manner in which a model speaks, but grounding dictates the factual parameters it is permitted to use. Even when equipped with basic retrieval systems and natural language chain of thought prompts, language models continue to stumble on multi-step reasoning tasks. The root of this failure lies in the medium of instruction. Natural language is inherently ambiguous, filled with nuances and structural imprecision. When an LLM attempts to describe intermediate reasoning steps using natural language prose, this textual ambiguity disrupts the model's rigid inference logic, causing it to lose the thread of complex problems. Evaluations conducted on the GSM-8K arithmetic reasoning dataset provide concrete statistical proof of this breakdown. Models using manual, natural language chain of thought prompts to solve these math problems achieved an inadequate maximum accuracy of just 46.6%. To correct this reasoning deficit, engineers must stop communicating with the model as if it were a human and begin programming it like a machine. This necessity led to the development of the COT-RAG framework, a three-stage architectural solution designed to enforce absolute logical rigor. In Phase 1, human experts construct a coarse-grained decision tree. This maps out the foundational reasoning logic required for a specific domain, independent of any single user query. The language model decomposes this human logic into a knowledge graph of delineated entities with explicit relationships. Each entity contains a sub-question, sub-case, and sub-description to eliminate linguistic ambiguity. In Phase 2, case-aware retrieval dynamically pulls external data to populate these sub-descriptions exactly when a query is submitted. The framework delivers an expert-constrained logical graph directly into the model's inference window, providing a rigorous navigational map that guides the LLM through every step of the query. The final phase dictates exactly how the model processes this graph, utilizing pseudo-program prompting. Instead of allowing the model to output reasoning steps in natural language prose, pseudo-program execution forces the LLM to output logic as structured code blocks. This side-by-side comparison merges the vast versatility of text with the logical coherence of a programming language. On the left, lacking syntactical boundaries allows the model's reasoning to easily drift into hallucination. On the right, rigid syntax rules establish physical constraints, preventing logic from straying. The pseudocode acts as a mathematical cage, restricting the stochastic parrot from flying outside the bounds of factual execution. Deploying the complete caught-RAG pipeline has yielded massive empirical performance gains across multiple public datasets. In evaluations spanning diverse reasoning tasks, the framework achieved accuracy improvements ranging from 4.0% to 44.3% over current state-of-the-art methods. To build reliable artificial intelligence systems, the software industry must stop treating the language model as an omniscient reasoning engine. It is highly effective as a simple execution layer, provided the reasoning framework is architected entirely around it, using structured retrieval and graph-based grounding.